Thank you so much. So now this would be a long session, like 90 minutes. I hope you had a great lunch and you'll not feel sleepy. So what we'll do is, how do we break the session? I have a presentation and I have a Python notebook for demo. You can also clone my GitHub if you want to play around along with me. But since it's a very new concept, I would appreciate if you pay attention to how we are doing, and then I'll share the notebook later after the presentation. Okay, so please feel free to ask any questions if you like. We will have maybe 3 breaks between the sessions, one after the presentation, one between the notebook session, and one at the end. However, in case if you have any doubts in the middle, please feel free to ask. Okay, so when you talk about how to make machine learning fair and accountable, the entire concept of fairness in machine learning is very, very new. We must have heard about what is machine learning, what is explainable AI, but when it comes to machine learning fairness, it's very, very new. So what are we talking about today? We are talking about the need for fairness in AI for financial services, detecting bias in AI model. So the main thing is, how do you detect bias? Then removing bias throughout data science lifecycle. We understand what is a data science lifecycle, from data ingestion to prediction. Then fairness matrices. How would you measure, quantify fairness, and how do you ensure that your algorithm, data, and prediction are fair based on various mathematical definitions of fairness? Then we'll talk about data fairness, how to make sure your data is fair. Then we'll talk about accuracy cost fairness trade-off, that if you apply fairness, will your accuracy go down or not? Will your cost go up or not? We'll see the trade-off. How can we manage the trade-off? What would be the optimal value and things like that? And then model fairness for multiple bias. For example, if you have multiple features which are biased in your data, not one, how do we tackle that? In classification algorithm, we understand what's 2-class classification algorithms, and in regression. So maybe one continuous variable kind of thing and one binary variable kind of thing. Post prediction fairness. So if you have done everything and you are at a stage where you just want to not make a model, do not want to touch your model, but just want to make your prediction fair, how we can do that, and demo on a credit risk data. That would be my Python thing. However, I think after part 4, I'll switch to the notebook and then come back to the presentation later on, right? Okay. The need for fairness in AI. Now, before we talk about what is fairness, let's see how do we define fairness. So I guess most of you must have heard about this Apple Card fiasco which happened recently, where women were given 10 times less interest, or maybe the less credit limit than men. And it was a huge fiasco which happened, and it was everything went up on Goldman Sachs. Like they made the algorithm, and the algorithm was not able to do a fair decision and things like that. So that is what is fairness. The ability of an algorithm to treat various groups equally is what is fairness. So if you have an algorithm, in simple terms, let's say this way. So if you have an algorithm, say a classification algorithm, the accuracy of the algorithm is 90% on various matrices. Maybe AUC is high or true positive is high. The accuracy is 90%. Now that model is really very good to go in production, right? Now, what if you open the model and start seeing accuracy for different groups? So if you see accuracy for married men and single women, or married men / divorced women, you will find the accuracy of the model is 95 for men and maybe 85 for female. Now that is where bias comes in, right? That is what we are talking about, that the algorithm has no right to differentiate between men, women, married, unmarried, number of dependents, no kids, race, nationality, based on accuracy and other things. So that is what we are talking about. The ability of algorithm to treat various group in the data with without any bias. That is what we call fairness. Simple fairness is also known as equality of odd, disparate impact, parity ratio, equal opportunity, odds ratio. Now what are these? We'll go into these details. We'll see each of these metrics and we'll see how to measure them, how to calculate them, and so on and so forth. So what are different kind of bias which can happen? It can happen because of color, if you have any color as a feature in your data, gender, race, age, marital status, and nationality. Now interestingly, even if you don't have any of these, you still can have bias. So in one of my company I was working in long time back in an e-commerce firm, so we did not have something called gender or marital status in our data. However, if you understand, in most of the e-commerce company, you have differential pricing strategy, that you have different price for different groups of people. So what we did, we took out chocolate consuming habits or chocolate purchasing habit, and we found out who is a male and who is female. So even if you don't have all this, you still can find out, you can have proxies for predicted variables. So first name can be used to find out race. There are few racial groups whose first name are pronounced or written in a very particular way. Zip code is one of other thing. There are zip code which has domination of one particular group of race or nationality. So even if you don't have any of these, you still can have bias in your data. And not only this, you can have a linear combination. You can have, say, chocolate eating habit, the type of purchases, frequency of purchases, and zip code combined together can tell you everything about gender, race, age, marital status. Right? So even if it is not visible in your data, hey, I don't have color, gender, race, age, marital status, or nationality, you still can have bias in your data. Right? Okay. This is interesting. So I have this was this research done wherein they used 3 very renowned face recognition apps, which was Microsoft Face++ and IBM. Now what is interesting to see here, if you see light color male, the accuracy is almost 100%, right? So if you put a picture of a light color male, the facial recognition software will recognize it as a male with 100% accuracy. The moment you put a dark color female, you see the accuracy actually goes down to 79%. Same algorithm is able to recognize faces of one group with complete perfection, 100% complete perfection, and of other group with around 80% accuracy, which is 20% decrease. So that is one thing which comes in bias in facial recognition. So we are talking about image. Moving from image, we'll talk about very interesting thing. Number one is, in India there is this company which used to decline loans to women because it gave more weightage to, say, salaries which they got or the promotion which they got, and predominantly or historically we know that there is a wage gap. Women in Asian country and most of the country are paid less than the counterpart, female counterpart, and that is why they started rejecting the loan without giving higher weightage to feature which talks about loan payability, that is they do not default. But that is how it happened. Similarly, hiring decision favored male. You must have heard about this Amazon fiasco, wherein any application which had the word male, woman, female, lady were absolutely rejected by the algorithm. So even if you are a male and you're writing that I volunteered for all women community service, your application would have got rejected. Now that resurfaced and Amazon stopped using it. And the third thing is Google ad. So Google ad showed high paying jobs more to men than to women. And if you see the ratio, it's 1,852 times to male group compared to 300 times to female group, assuming that female would not qualify for high paying jobs. That is what Google ad did. So that is what we're talking about, bias in various things. So if you talk about financial services, you talk about hiring decision, you talk about ads, we saw something in facial recognition, and then we'll see something more. So if you see here, so this is nothing, this is a simple statistics which shows that how African American compared to Hispanic or Asian compared to white applicants, had to face a lot of bias when it comes to loan or mortgage applications approval. Similarly, recently Bank of America had to pay around 240 million pound fine to regulators because they were not giving loans, or they were disqualifying, or they disqualified around 200,000 qualified African American and Hispanic borrowers just because of their race. And this is a very recent thing which happened. And if you want more recent, here it goes. Few weeks back, Apple Card was found to pay lesser credit limit to women than men. And this is the actual tweets, and this person, Steve, is actually working in Apple, who was actually kind of a whistleblower. So that is where we actually try to conceptualize what is fairness, what is bias. We are not trying to improve the society, but we are trying to make sure that whatever bias is in society does not come to your algorithm. Or algorithm does not, you don't give power to your algorithm to create discrimination and bias. Right? Okay. So as we talked about detecting bias in AI models. So before we talk about bias, we need to understand there can be set of few questions which we can ask ourselves, which we can ask at the, at the beginning of data science project, which will allow us to understand that do we have any kind of extrinsic or intrinsic bias in our data or not. So these are few questions which we collated, which you can ask in your data science lifecycle at the beginning of a project to understand, does your data science have any kind of bias or not. Or now, before I move on to the next slide, if anybody would like to ask any questions. No? Okay. So we'll move to the next slide. So removing bias throughout the data science lifecycle. Now this is a typical high-level data science lifecycle where you have input data, where you do some kind of pre-processing. So on data, I check for bias, I treat the bias, then I go to my modeling stage, I check for bias, I treat for bias, then I come to my prediction stage, which is an output stage. I check for bias, treat for bias, and then do a cost, accuracy, fairness, trade-off optimization. You may not want to make fairness 0 if your cost is going high. You may try to have some very less discrimination but reduce your cost or prevent your cost from going up. And that is where we will see, we'll take up all these 3 boxes and we'll see how to tackle bias, right? Now here we'll move to my, sorry. Okay, so here we move to my notebook. So this notebook is also on my GitHub. A part of this is on my GitHub. So if you would like to, where is my, okay. So there goes my GitHub. So you can actually clone this. Sorry. Oh. Okay. No. Yeah, this is my GitHub link. So half of the thing in notebook are blank spaces where you can put your own numbers, you can put your name of features and play around to see how does it work, right? However, the entire notebook, I'll show it to you here, right? So the session is, what we'll do is, we saw this data science lifecycle right now. I'll repeat. So we have this input data. We check for bias in input data. If we find bias, we use some pre-processing technique to remove bias. If not, we do our feature engineering, data cleaning, and move to ML model. Now, the very interesting thing is, when do we check for bias here? Do we check for bias on raw data or processed data? The most important thing here is, it's better to check for on processed data. Now, the reason is why. Sometimes there is no bias in your raw data, but the way you create feature, the way you do feature engineering may lead to creation of some features or variables which would have bias in it, right? So you may have linear combination of few variable which will lead to bias. So it's better to check for bias just before you put your data into a model. And then you have a model wherein you create a model. When your model is done, when your model is trained, when your model is tested, we'll take the model and check for bias in my model. If found, we will use some algorithm to remove this bias. If not, we will use that model for predictions. Once I get my prediction, I'll again check for bias in my predicted data. If I find it, then I'll use some kind of optimization algorithm to remove, or calibration algorithm to remove bias, or else I'll move down to, I'll use the data as is for my output. And it does not mean that you have to only use one of these steps. There can be a multiple combination. You may have to use the red box or green box, or the blue box and green box, or all the three boxes in the same sequence. It depends upon how biased is your data. Okay. So this is how we'll go. We'll load the library, we'll load and prepare the data, we'll explore the data, we'll detect some bias, we'll remove some bias, we'll do a trade-off analysis, we'll then go for modeling technique, then for prediction, and then there'll be something which talks about things. So these are basic libraries which we are all aware of: NumPy, Pandas, scikit-learn libraries, and that's it. And these two, if you see, the last two libraries are the functions which I have written, which would be used. Yes. You want? Oh, sure. Perfect. Yeah. Okay. So these are basic Python library: Plotly, Seaborn for graphics, a few sklearn model. Basically, I've used logistic and linear regression model. You can use any regression model or any classification model. And then these are two functions which I've written, which I'll be importing so that I can do my analysis test for thing. But I'll talk about this function in some time. Okay. So here I'm not doing anything. I'm just reading my data file and doing some transformation. After doing some transformation, I did one feature engineering where I talked about anybody less than 40 years old is young, anybody above 40 years old is old. So that is what I just made one feature, but will not be using this feature at all. But I just did it because I just wanted to show. So how do my data looks like? It has around 61,000 applicants, where we will see that will they default or not over 205 features or variables. Now, as we know, most of these are imbalanced data. So if you see, people who are non-defaulters are 46,000 and people who are defaulter are 14,000. Basic any credit default data, wherein you have more defaulters and more non-defaulters and less defaulters. Yeah. Anybody? Right. Any questions here? Perfect. So now we will see what is bias. So now this is what we need to understand. A protected group, which is denoted by capital S, is nothing but all the things which we talked about: color, nationality, gender, marital status, number of kids. All these are protected group. On those protected group, I'll try to analyze that do I have bias or not. Okay. The next one is called advantages and disadvantages group. In any protected group or protected feature, there will be two groups. One would be advantages and one would be disadvantages. Advantages would be those groups who have higher probability of a favorable outcome. So here, what is my favorable outcome? Here my favorable outcome is being non-defaulter. So those group who has a higher probability of being tagged as non-defaulter are called advantages or privileged group, and those group who have a higher probability of being tagged as defaulter are tagged as disadvantages or unprivileged group. And we understand what is actuals, which is my target variable, the actual data, and predicted level labels are represented using y hat. So these are the notation we will follow. Okay. So this is a very simple definition which is called statistical parity test. Now what is statistical parity test? If you see this equation, it talks about the probability of y equal to 1, that is the probability of somebody being tagged as non-defaulter when the group is TA, should be equal to probability of somebody being tagged again as non-defaulter when the group is B. That is, the probability of somebody being tagged as non-defaulter for male should be equal to probability of somebody being tagged as non-defaulter for female. So TA and TD is advantages and disadvantages. So the probability of you or anybody being tagged as non-defaulter for advantageous group should be equal to probability of somebody be tagged again as non-defaulter for disadvantageous group. Simple. So how do you define that? The first part minus the second part should be 0, or the first part divided by the second part should be equal to 1. Both should be equal, right? So here my favorable group is 0 and unfavorable group would be opposite, which is 1. And these are my capital S, which is my protected features, which are gender, which will see that male versus female, higher education versus non-higher education, young versus old, owner versus not an owner, mortgage versus not an mortgage, entrepreneur versus non-entrepreneur, tenant versus non-tenant, and Estonian versus non-Estonian speaking people, English versus non-English speaking people, number of dependent less than 3 versus not, married versus not, single versus not, divorced versus not, work ex less than 10 years versus otherwise, and work ex less than 5 years versus otherwise. And so I've just made a dictionary which talks about all this data. And then what I've done, I've called this function called statistical parity test, which I have written down myself, which is based on this logic, right? That the probability of advantageous group versus disadvantageous group for a favorable outcome should be same, and disparate impact, that both should be equal. So this is ratio and this is just a subtraction. So if you see this, so these are the numbers. So now if you see for gender, you will see that there is a statistical parity of 0.6, 1.09, and there are a lot of numbers. So now it's very difficult for us to go through all the numbers and see. So what we'll do is, first we'll read this. Statistical parity difference should be between 0.1 and minus 0.1 and plus 0.1. Now what is that? I am allowing 10% bias. That is, I am allowing that for you, if the probability of favorable outcome is 80, for me it can be 70 or 90. So plus minus 10%, right? Similarly, for disparate impact, the ratio should be 1, perfect, but I'm allowing anything between 0.90 to 1.1. So I'm allowing 10% disparity. Now why 10%? That's my business call. You can actually make it 5%, 10%, 15%, 20%. Now why I chose 10%? Most of the regulators recommend 10%. So that is why I chose 10%. However, there is no hard and fast rule that it has to be 10%. Right? Now, the same data which we saw right now, I tried plotting it, and here is the plot. Right? So if you see the red bars are statistical parity different, and black bars are disparate impact difference or disparate impact ratio. And if you see the dotted black line and the dotted red line are the threshold. So can we count how many variable or how many red bars and black bars are above their threshold? Can we see how many black bar or red bar are above their threshold? Or both? How many black and red bar are above their threshold respectively? Around how many? 4, 5? And if it is a bit above their threshold, you can ignore it. You say, okay, 12%, 13%. So something which is significantly above their threshold. 5. Right? So let's see. So it is clearly visible that there are 5 sensitive features: number of dependent less than 3, married, single, divorced, work ex less than 10 are having some kind of bias. That is, in those cases, the probability of having favorable outcome for, say, let's take married. For people who are married and people who are not married has a difference of more than 10. So for example, if people who are married have a probability of having a favorable outcome which is 80, the people who are not married have a probability of having a favorable outcome which is less than 70. Much less than 70, and it's actually very less than 70. If you see, the dotted line is 10%, plus they are around more 10%, so less, around 20-25% less probability. So that is what we are trying to see here, right? So it is easier for us to understand. So what we'll do, we will choose, before we go, so let's again, so these are distribution of data, how many married versus how many non-married. So if we are using marital status 1.0, which is showing me married or not. So if you see that a lot of people who are not married and very less people are married, the distribution is also less. Now if you go much down and I do a heat map, we understand what's heat map. So on the x-axis we have defaulters versus non-defaulters, and on y-axis we have married 1 and 0. So this graph. So when we talked about favorable and unfavorable, that favorable groups are those who have a higher probability of getting a positive outcome. So here if we see what is looking like a favorable group. So if you only see the x-axis, which number or which binary value represent favorable group, 1 or 0. Just add 47 plus 4 and 12 plus 2. So favorable group should be 0. So we should remember my favorable group is 0 and unfavorable group is 1. Right? Now, which is my privileged class and unprivileged class? Which group, marital status 1.0, being tagged as 1 and 0, which has a higher probability or representation of a favorable group? So now forget the 0 column, just see this 2 column. So which tagging has, looks like a privileged group? 0 or 1? Anybody? Given that my default 0 is my favorable outcome, which is my privileged class? Which is a higher number? If in this heat map, which has the higher number? Yes, 0. So if you see 42,709 is the highest number and which belongs to a favorable class. So this is my advantages or privileged group, and this is my disadvantages and non-privileged group or unprivileged group. So we understand 0 and 0 are my favorable and privileged class. 1 and 1 are my unfavorable and unprivileged class. So using that, we will go further. So I've chose this. So if you see your notebook, this line is blank. You can put any features which you want or any variable which you want. So I have selected something called marital status 1.0, which is showing that a person is married or not. Privileged value we just saw is 0, and unprivileged is opposite of 0, which is 1. So I'm using this 3 thing as my input to decide to go forward, right? Now before we go forward, anybody would like to ask something here? Right. So how many of you are looking at the notebook? Oh great, so you have cloned it. Okay, great. So the notebook is a summarized version of what I'm showing. I'll put this notebook later on. So you can choose marital status 1.0, but interestingly try to choose something else, because 1.0 result would be on the screen. So try 2.0, 3.0, home ownership, and there are a lot. WorkX, try to put in any feature which you want. And to see what is my privileged group, should be 0 or 1, please refer to this heat map. There can be chances where privileged group is 1. So I'll show you one of those. So if you see marital status 3.0, this is 0. I think so this one. 4.0, my privileged group is 1. Because for 0, the higher number is on 1. right? So you have to be very, very careful when you put your privileged and unprivileged. Even if you're not careful, there's nothing would happen, everything would be negative. So you'll, instead of getting a positive number, you'll get a negative, right? Okay, so what we are doing here is, we are doing same thing, so we again got the same result. So here we see the statistical parity test for sensitive feature married is more than 0.10. Let's say, is it more than 0.10? Yes, it's 0.13, which is more than 1.10. So we allowed 10% bias, but there is a 13% bias. And similarly, in disparate impact, we allowed, it should be 1, but it is 82, which is around 18% bias or 18 points of bias. So we can actually say there is something wrong in my data. So so I'm not concluding that there is a bias or not. I'm saying that this requires further investigation, right? And let's investigate. So again, remember, statistical parity should be between 0.1 and 1, and disparate impact should be between 0.90 and 1.10. These are your numbers. You can define your number at the beginning of the project, not after doing the test. Okay, anything before we go forward, before we try to investigate? So we saw two matrices. One is statistical parity test and what is disparate impact, which takes your original data. So I just took the actual Y variable, I took your sensitive feature married and just made a heat map and did some mathematical calculations. That's it. There is no rocket science here, right? Okay. Now we'll do something called a Reeving technique. Now what is a Reeving technique? Now what is a Reeving technique? How many of us knows about something called a loss function? Most of us know about loss function. So anybody, what's loss function? What is the objective of a loss function? Is to reduce my error, right? Now in this data, if you have more men and less female, right? What would dominate your loss function, male or female? Male. So any error in female would be represented in less quantity, but any error in male would actually inflate your loss function heavily, because there are more male and less female. How can I handle this? I can handle this by telling my loss function, hey dude, if you are making any mistake for male, I'll punish you by 1 point. But because you have more male, but the moment you make any mistake for female, I'll punish you by 5 points. That's it. So I'm giving weights to each of this combination. And to make it further complicated, I'll say that I will punish you with a point when you are doing any error for male belonging to favorable group. I'll give you with point, I will punish you with point B or penalize you with point B. If it is for male, for unfavorable group, I'll punish you with point C if it is for female favorable, and point D for female unfavorable. So I can give you 4 weights, and I can tell you that if for each of this combination, I'll do a weighted loss function, I'll do a weighted penalty, right? So anybody who did not understand this concept? Yeah, so great. Okay, no. So I'm taking your algorithm, let's say logistic regression algorithm. It has something called a sample weight. It is a parameter called sample weight. So for all the sample weight, wherever it is, say male favorable, I'm giving some weight. For male unfavorable, I'm giving some weight. For female favorable, I'm giving some weight. Or female unfavorable, I'm giving some weight. So when the model is doing something called a gradient descent and doing some loss function or a cost function, it will multiply that cost for each of this row with the weight I am giving. So I am saying that anybody who is female and is favorable, I will give you highest penalty. So for others it can be 1, 1.5, 0.6, here it will be 2. So that if you make one single mistake here, you will be penalized more. So gradient descent, please be careful. You have to make sure that this part is also very, very accurate. The way I started, that the accuracy of the model should be equal for all the groups. Not that overall it is very high, for male it is very high, for female it is very low. So I'm trying to penalize the function to ensure that my accuracy is stable. Right? Okay. So we also use this term accuracy, cost, fairness, trade-off, right? We did in initial part that when you try to make a model fair, there can be chances that your accuracy can go for toss, and when your accuracy go for toss, your cost may go up. Now what is cost here? Cost is nothing but a pound value of your project, right? How do you calculate pound value of your project? For any false positive there will be a cost, and for every false negative there will be a cost. Now what is false positive? False positive, if I give a loan to somebody who will not pay me back. False negative is I did not give loan to somebody who would have paid me back. Simple. So which is more expensive for the bank? False positive or false negative? False positive. So I have a cost of 700 pounds for single false positive and 300 pounds for a single false negative. And using that, I'll go further. I did some calculations, and these are my weights. So how do I show you? Okay, these are my weights. So for P, so privileged favorable, my weight is 0.98. Privileged unfavorable, my point is 1.06. Unprivileged favorable is 1.18, and unprivileged unfavorable is 0.66. So which combination has the highest weight? Unprivileged and favorable, and that is what we were looking at. For all people who are unprivileged, we wanted to have for them to have a very good favorable outcome. Now we are saying that anybody, if you make a mistake for unprivileged and favorable people, I'll penalize you maximum, which is 1.18, because I'm more concerned for giving right decision than wrong decision. Right? But for you may argue that this for this use case. What about cancer patients or anything else? Then you can actually reverse the entire thing. For there you want to optimize something else. Here I'm trying to optimize favorable and unprivileged group. Right? So this has the maximum weightage. Now how do I use this weight? I take all the row, I create a new variable which is called new weights, and just I'll paste those values against each of these row. For any combination, whatever is the combination, I'll put those values against it. So I'm just creating a new feature. Neither I'm changing my data, neither I'm increasing my data, which is oversampling, neither I'm decreasing my data, which is undersampling, but just putting a new row to the entire data set to make sure that I can use it. Right? We talked about this, I guess, that this is what? In a generic machine learning algorithm, increasing sample weight should increase the effect of training on sample. That is, when you have a loss function, it will penalize the loss function with higher weight and vice versa. Now this is what we are doing. So we are making one simple logistic regression model without taking the weight. So I'm taking CLF WOW, which is without weights, making a model and training that model. So the accuracy of the model is 75% and the accuracy difference is 13.86. Now what is the accuracy difference? Accuracy of male versus accuracy of female. Here accuracy of married versus accuracy of non-married people. Let's subtract them and see my answer. So the accuracy difference is 13.8 and overall accuracy is 75. So overall the accuracy is very good, 75, but if you take the accuracy of married versus non-married, there's a difference of 13%, right? Which we also saw in statistical Parity test, the value was minus 0.13, right? So if you see, everything is coming together. So anything before we move forward? Any questions here? So did anybody use some other feature in their data and run the notebook? No, okay, leave it, we'll do it later. So I have all the outputs with me at the end, we'll show you all the outputs. Okay, now what we'll do is we'll just pass the model based. How do we pass this model based? How many of us recognize this command? Simple logistic regression scikit-learn command? Very simple. We understand X train and Y train. What I have done, there is a parameter called sample weight. I've just passed the weights here, nothing else. I'm neither changing the data, neither changing the algorithm. I'm just passing the weight and I'm calling it CLFWW, that is with weights. Now when I have with weight, what is my accuracy? 75.7592 and accuracy difference 13.377. So did it decrease or increase? We don't remember, so here is the table. So with weights, the accuracy is 0.7583. Sorry, without weights, the accuracy is 0.7583, and with weight, it is 0.7592. So is it a good thing or not? We increased the accuracy, but that was not the goal of the entire session. The goal is to decrease the fairness. So have we decreased the fairness here? The difference between male and female accuracy initially was 13.86, now it is 13.77, which has decreased. Thus it is a good thing. However, so this is a win-win situation. My accuracy goes up, my fairness goes down. However, this does not end here. So why? I am taking accuracy as what? True positive plus true negative, the entire confusion matrix. But you would argue that what if I'll take AUC? What if precision? What if true positive, recall, other thing? I would like to measure my accuracy on other metrics, not on the matrix which you just showed. So we can even do that, and here it goes. Can we see? So I'll just reduce screen size a bit more. Okay. So here it goes. So the red bar are accuracies, difference with weights, and the black bar are without weights, right? So the first one talks about AUC, area under the curve. So for married versus non-married, we take both AUC and subtract them together, right? So which of I guess 1, 2, 3. Out 8 or 9 matrices which are in my favor and which are not in my favor. Anybody, how many of them are in my favor? So in how many cases the red bar is smaller than black bar? That the difference is less compared to the black bar. With weights, the difference should be less between men and female compared to without weights, the difference should be less. What is the difference between married versus non-married? In how many cases do we have red bar smaller than black bar? 3, 4? 5, great. 5 out of 9, which is a good number, right? And interestingly, false negative rate, you will say it's higher, but false negative rate should be higher. You don't want false negative rate. So precisely 6 matrix out of 9 are in my favor when it comes to accuracy. Right, and I have used, I guess, almost all possibly commonly used accuracy matrices which you used in any binary classification algorithm. AUC, Gini, precision score, precision, sensitivity, false negative, F1, and total cost. And cost have also gone down. If you see the red bar, the cost have gone down. Right, so false positive plus false negative, I told you the costing 300 and 700. I did the same thing, and you see the cost going down. Right, so this is still a win-win situation for me. The first case when we saw that was a win-win situation. Here it is again a semi-win situation because it's not 9 out of 9, it's 5 or 6 out of 9. However, we have still not defined fairness. We are talking about everything on accuracy. That the accuracy of the model should be good, the accuracy difference between married and non-married should be as narrow as possible, everything. But still the word fairness did not come in the entire session. Now this is the time when the word fairness should come in. Right, so can we read at the end? I'll maximize it a bit. Right, so now these are 8 fairness definitions. So one is called average odd ratio. So average odd ratio is the difference between false positive rate and true positive rate. That the difference between false positive rate and true positive rate for both the group. advantages and disadvantages should be same. That's called average odds ratio. The next one is equal opportunity, that the opportunity which you give me, right, should also be given to other. Now what is the opportunity? Opportunity of being y equal to 0 when y equal to 1, and so that is the prediction should be 0 when the actual is 1. The probability of that should be same for both the group. That's equal opportunity. This is false positive, right? When your prediction is 0 but actual is 1, right? Predictive equality is just the opposite. When your actual versus prediction, so y and y hat should be equal. Equalize odd, so the prediction should be 1 when y equal to 0, first case, and prediction should be 1 when y equal to 1 in both the cases. If you make mistake for me, you make mistake for others. When you don't make a mistake for me, don't make a mistake for others. So you penalize both of us equally and you reward both of us equally. That is equalize odd. Treatment equality is nothing but false negative versus false positive is a ratio. So if you see, most of them would overlap with each other. So which one to choose is again a business call, right? Most of the time what we choose is equalize odd and equal opportunity. This two covers everything. So this is like for false negative, and equalize odd is true positive and false positive. So you cover almost everything. Demographic parity, y equal to 1 irrespective of my demographic. We'll see this, that if I am a male and you gave me a result that I will give you a loan, I'll use the same thing but change Sray from male to female, and still you have to show me that you are giving me a loan. That is irrespective of my protected attribute gender, the result should be same. That is demographic parity. So we will use all this, and here is the data. So I'll just reduce this. Oops. Yeah, so this is here. So I have mixed a lot of things here. I have few important accuracy matrices and few important fairness matrices. So here again, the red bar should be smaller than the black bar in all the cases. So in how many cases, I don't know how many are there? 1, 11. Out of 11 metrics, in how many cases are they in favor of me? 11, right? 10, okay. So out in 10, basically 9, the last one is cost. Or let's take it 10. Cost is also made, right? Out of 10, how many are in my favor? Let's say, in how many times the red bar is smaller than the black bar? Out of how many? There's 10. 8 out of 9. There's 9. No, there are 10. 9 out of 10. I see 9 out of 10.
You said we don't take cost.
Okay, forget it then. So almost a very good percentage. Except for area under the curve, everything is in my favor. And even for area under the curve, it's a very nominal difference. A very nominal nudge, that is a small decrease. So we see that, and we told that we'll concentrate on two things. One is equal opportunity and equalize odds. So 1, 2, 3, 4th and 5th, we'll concentrate on 4th and 5th and total cost. So here if you see, my equal opportunity has decreased phenomenally, and equalize odds also have decreased phenomenally, and the cost have also gone down by few notches. So my business is happy that, hey, you made my algorithm fair, but I don't have to incur more cost. You have actually saved me from false positive and false negative cost. That they are happy. You are happy because the regulators are happy because equal opportunity and equalized odds have gone down, and other predictive, and you were already happy when your true positive precision and everything was also maintained. Right? So it's a very good win-win situation. Now, still there is a problem here. Now what's the problem? whenever we do a binary classification, we choose a threshold, right? 0.5 is a default threshold. That anybody above 0.5 are defaulter, anybody below 0.5 are non-defaulter. Your business comes and says, hey dude, I don't want 0.5. I say that's so lame that every time you come with a logistic regression, you say 0.5 defaulters and using 0.5, you made your confusion matrix and you showed me everything. A very good thing. But I do not agree with it. Tell me a threshold wherein I'll be able to optimize everything, but it should not be 0.5. Tell me a better threshold. I want more. So he becomes greedy. He comes and say, hey, I want more cost reduction and more fairness reduction and a higher accuracy. Now give me a threshold which gives me more cost reduction, more fairness and more accuracy. So now what do you do? So initially we always use 0.5. By default logistic regression gives me 0.5. So what I do, I try to optimize. Now there comes, so this graph. Can we see this graph? I'll decrease the font size. Now can we see this graph? On one side of the graph is my total cost, because it's very, very important. No business would agree on any fairness technique if the cost goes up. So you want the cost to go down. And on the other side, you have all the other matrices which you wanted under the sun. All. So from all your fairness matrices to your accuracy matrices, I'll zoom it a bit so you can, let's see. So these are all equalized. Even if you can't read this, so here it goes. All. Can you read this? Equal opportunity, equalize odd, demographic parity, average odds, predictive equality, TNR, precision, FPR, F1, AUC, sensitivity, FNR. You have everything. Almost all. Right? And then I made this graph. So now, when I make this graph, which, I'll zoom it a bit more. Okay, which threshold, not one particular threshold, what should be the range of threshold which you as a person would accept where the cost is low and almost all these things are near to zero. So of course the fairness should be near to zero. The difference in the fairness should be near to zero and accuracy should be near to zero. What is that range of threshold? It's like where does the cost go up? From where? I think so 65, 70 the cost goes up too much, right? So anything, it should be below 75. So if you see anything below 75, where do you see that everything merges towards zero? Everything is, all these matrices merges towards zero. So if you see something between 0.50 to 0.70 should be your threshold limit, right? So if you see this nicely, and see there's a lot of lines here. You can choose one of those lines and optimize it. You don't have to choose everything. You can choose one fairness, one accuracy, one cost and optimize everything. So you can actually go through all the values and optimize. Now there's one more technique which I don't prefer ever, which is itself discriminatory, that I'll have a different threshold for male and a different threshold for female. Now which itself is discriminatory, having two different thresholds, but still you can do that. So threshold privileged, threshold unprivileged. So anything between 45 to 55 for privileged and anything between 35 to 40 for unprivileged would be an optimized threshold. Okay, so this is it. Now before we move to so this what we did, we only played with the data. We did not touch our model, did we? No. So we just took our data, we added a new feature which is called weights and used the weights in a logistic regression. We took the output, we saw it across across various threshold and did. Now that was the most simplest part and something which anybody can do after knowing how it needs to be done, right? Now comes more complex part, which is how do I make my model very, very, very fair. Now before I get into my model being very fair, anybody, any questions here? No? Okay, yeah. So.
Yeah, at one point where you compared the F1 scores. So the F1 score was around 0.1. So I don't think the model which you have created is good
No,
in terms of.
absolutely. So here we are not trying to make the optimal model. I have not optimized the model at all.
Is it you only using only one feature?
Yes.
Only the married column.
No. So they are all the feature plus one protected feature married.
So you have applied.
I have not done feature selection. I have not done anything. It's just a vanilla model. So all this also, the accuracy of all this depend upon how good is your base model. So if you try to optimize logistic regression, you will do feature selection, you will create more features, you will do all this thing, your model will become better. Your AUC will go up, your F1 would go up, everything would change. These are all vanilla.
And the time when we were counting how many of the metrics are better, so the AUC was more.
Yes.
For the with weights.
So it's not AUC which is more, the AUC difference between male and female.
That's the difference.
Yes. So AUC difference for all the male, AUC difference for all the female, I divide. It should be 0. But we are seeing that it was not 0. But with weights, it actually was less than without weights. Okay. Okay, now let's see this. So this technique is called additive counterfactual fair model. Now, how many of you have heard about counterfactual fair model? I just talked about counterfactual fair model, that everything remains same. If I change myself from male to female, what's that? What's the output? That's counterfactual. That is, take the fact, make it counter, which is counterfactual. Why additive? It's just not gender. I'll take gender, nationality, married, all the other things. So that's why it's additive. Additive talks about multiple bias. Counterfactual talks about taking the fact and making it counter. Okay, so these are my sensitive features, these are my independent variable, and this is my target variable. Now, why I'm showing you a different technique, you will just see it in a while. How do we do that? I make a full logistic regression model. So what I do, I take the entire data set without considering what is my, sensitive and what is my non-sensitive. I take all the features, everything, and make a logistic regression. In the second case, what I take, I take all my sensitive variables separately, and if you see this, what I'm trying to do, I'm trying to take all my independent variable and trying to make a model with all my sensitive variable which can predict my independent variable. Right? So anybody, so if you pay attention here, you'll understand. I'm trying to see that how good my sensitive variable defines my independent variable. That is using number of dependent, single, married, divorced, all these three features. How good am I able to define or model age, applied amount, expected loss, liabilities, income, interest, loan, and monthly payment. That's it. And then what I do, I take the residuals. So what I do, I make a model which is based on my sensitive feature and then take a residual showing or basically taking out the correlation between age and my sensitive features, applied amount and my sensitive features, expected loss and my sensitive features, and so on and so forth. So I'm now just taking those values which are very raw, which are completely independent, which cannot be explained by my sensitive feature. So I'm making all of my X variable independent of my sensitive feature. We know that there's something called multicollinearity, that one variable explain other variable, which explain any other variable. So I'm taking out the effect of sensitive or protected feature from all my X variable and then making a model. So after which I make a model, I still see that my equality of opportunity, equality of odd have gone down phenomenally. Like it's almost zero. This is what I wanted. Initial case, I did not do anything. Here I just changed the way I'm modeling and I actually made my equality of opportunity and odds almost zero. Almost, if you see, almost everything is zero except for precision and predictive parity. Right? But the question is, why would I use this when I already have a technique? Right? Why should I use this? So this is just an option, but where do you use this? What is the best place to use this is when you do a continuous variable thing. So when you have a continuous variable, when the outcome is not 0 and 1, which can be how much loan should I give to? Or for example, the Apple card, limit. How much limit should I give to a male and female? So it's a continuous number, 100, 200, 300, 350, 360, 370. So I can make a distribution. So if you see this distribution, do you see the distribution are very different for male, married and non-married in this case? It's actually very different. The lines are the mean value. The average of all the value for male and the average for all the value for female predicted by logistic regression is still different. And if you see, the mean, skewness and kurtosis is also very, very different, right? So that is how we define our distribution. Now if we go forward, this was in my actual data, the actual Y value. Here also it is different. Logistic regression did a bit better job, but if I use the additive counterfactual model, what I see is the red line has gone. Why don't we see the red line here? It's basically merged because the mean value, the average for male and female here, married and non-married, is equal to 0. There is no difference between male and female. The kurtosis and skewness is also very, very similar. So if you see, the height of the distribution is almost same. The width of the distribution is also same.
But what happens if you have like very extreme values?
Yes.
Then medians probably won't be superimposed.
Absolutely. In that case, you first remove the outliers. I told you, I did not do any treatment. It's a vanilla model. Here, if I try to do that, I'll focus more on modeling than on fairness. You remove your outliers, you do your missing value imputation, and you'll be able to do it. However, the distribution, the mean may not be 0, but it will be close to 0. It will be better than whatever it was, right? So if you see this table, which shows you in the data, the difference between mean was 14.3. In the full model, logistic regression, it was 13.5. In ACF, it was 2.8 to the power e to the power 14, which is 0.14 zeros followed by 2, which is 0. If you see skewness, 72, 90, 49, reduced. 99, 1.92, 44, again reduced. So my distribution have come very, very close to each other. And that is what we did. Now, still the story is not over. I still told that I want to concentrate on this line. This line. What would be my prediction if all health causally equal, I was member of another protected group? So if I take all my members, all my clients, all my customer, change all this, flip the values of all the 4 sensitive variable, what would be my output? Now before we go into this, anybody would like to ask anything here? So this is not in the notebook which I have shared. Yeah, the notebook was only the first part. Anything here? Okay, so let's see. So here what we are doing is very simple. So let's understand what we first make a logistic regression model with actual data and take out their actual values. And we have the predicted values. So we take a logistic regression model with the actual data, everything as is. We take out the residual, which is actual minus the predicted value. Do a sum, which is the sum of residuals, and take out the value. That the error of my logistic regression for everything as is x. Then I'd make the same logistic regression model, but change the value for all the sensitive variable. For male it become female, for married it will become divorce, for divorce it will become non-divorce, for number of kids more than 3 it will become less than 3, and again make a logistic regression model. And again get my prediction, again get my actual, and again get my residuals. And I subtract both the residuals. That is called my CUF, counterfactual unfair score. So that is my CUF. That's for logistic regression model. Similar thing I do with my ACF model. I take the ACF model using the as is data, take out the residual, again take the ACF model with counterfactual data, take out my ACF model, see the CUF value. Now I want to see which CUF is lesser. Now why I want to see my CUF is lesser? Anybody? What is the concept here? What's going on here? I'm trying to see that my model should predict the same values when I inverse the data. So the residual should be 0. That is the actual versus predicted residual while the everything is as is, and actual versus predicted residual, when I inverse, both should be same. The residuals should be same. That is, my prediction in the case 1 and case 2 should be equal. That is. So anybody, any doubts here? How many of you didn't get this? Anybody who didn't get this? Okay, how many of you got this? Oh, a lot of you got this. So you want me to repeat this again? Okay. So I make a logistic regression model, very simple model with data as is, take out my predicted values. Let's only take out my predicted values. I make another logistic regression model with all sensitive variable countered. That is, I change the facts. Like all zeros become 1, all 1 becomes 0. I take the predicted values and see that both the predicted values should be same. Yes. It is ACF, but a what we call a different version of ACF. In the first case, I did not reverse the values. I kept the values as is. Now I am reversing the values. I am making all male.
So you have one which is the possession then one with the sensitive variables.
Same, both logistic regression.
Yes, sir, both. Okay, and then you have the HCF model, which is, from what I understood, is just the same data with the sensitive variable again.
And as is. And then see the difference, both the difference, which is where the difference is. So if you flip it here, and if you flip and not flip, and if you see in the first case, flip minus non-flip, here you only have flip. How do you compare? So here flip minus non-flip, flip minus non-flip, and you see that flip minus non-flip is X, here flip minus non-flip is Y, which is less, X or Y. Right? So when I do flip, so when I do non-flip, my prediction is say 1,000 pounds. Example. When I flip, it is 1,100 pounds. Difference is 100 pounds. Now I'll go to ACF. Here, if I not flip, my is again 1,000 pound. But if I flip, it is 1,000.001 pound. So the difference is much lower. Then I can conclude that, hey, it does not matter if you have gender or marital status or number of kids, because the value predicted stays same or very close to each other. So that is what I am doing here. It is very simple. I am trying to show that does it matter having gender? Change my gender, it does not matter. So if you go to a bank and say, hey, you declined my loan because I am a male, he'll say, no dude, I made you a female and you still haven't, we still declined a loan for you. Right? So that is where. Similarly, it's like, Apple Pay. If there's this very interesting case, this guy went and told the court that my wife earns more than me. All other credit card gave her higher limit. Why the hell you gave them her a lower limit? They told, no, there is a wage difference. Then he told, my wife earns more. What wage difference? Right? Then they came out, it's because of gender. If Apple Pay to have showed that, oh, now change your wife's gender to make your wife husband and make yourself wife, it remains same, then the fiasco would not happen. So that is what we are trying to show here. So we took logistic regression in ACF, you took any model under the sun. You take random forest, you take deep learning, neural network, SVM, anything. One pair of that model, one pair of this model. And with ACF, interesting thing is, ACF is not dependent on the model. What are we doing with ACF? I'm making a base model. I'm making my I'm predicting my X features using sensitive features, other sensitive variable. You use any model. Use any damn model. I'm not saying that you have to use linear regression. You just have to first make the entire model, then take all the independent X variable with all sensitive variable, make another model, take the residual, make the main model. Here we are not saying, so all this concept are model agnostic. You don't have to go for a linear regression or logistic regression. Why I use linear regression or simplicity? It's very simple. It will not take much time to compute. And I did not even tune my model. You tune your model, it will be much better. So remember, all this output would be as good as your base model output. If your base model is garbage, everything is garbage. So garbage in, garbage out. So in this case, if you see, here, I'll show you the graph. So here it goes. So if I counter and non-counter and flip, the distribution is exactly same. The mean is almost equal to each other. So the red bar is when I flipped and the blue bar when I did not flip. So blue bar is with all the customers as is data for all the 4 predicted features, and the red is when I flipped them. So it's almost same. And for logistic regression, if you would like to see, this is the graph. The moment you flipped, the distribution went for a toss. The distribution changed, almost changed. So that is what, so see this difference and see this. This is much better than the previous graph. Right? And this is for the thing. And the last one is reject option classifier. Now before we go here, we have around 30 minutes, not even 20 minutes, I guess. Right. So any question, this will take 5 minutes for me, but let's have a small break for questions and then we'll go here. This is the most simplest technique and will be the most useful technique. Most useful in your life. Anybody else? Any questions here? Okay. So we'll come back to the first part. So when we talked about logistic regression, we told that it is a series of probability from 0 to 1. And we have this cutoff that anything below 0.5 is favorable, defaulters, above 0.5 are non-defaulters. Perfect. So when you talk about this 0.5 value, anybody around 0.5 are dicey people. They may be, may not be, because it's very near to the decision boundary. Anybody away from 0.5 towards 0 or 1, you are very sure that he is a defaulter, not a defaulter. Anybody around 0.5 is a dicey thing, right? So we'll take a 0.5, we'll make a circle, we'll see the length of the circle, we'll take the circle and we'll flip everything. So for all people who are defaulter, we'll make them non-defaulter, and all people who are non-defaulter, we'll make them defaulter. And we will make a model. It's very simple. So in this case, the total number of people inside this circle was 1340. People who were unprivileged were 261. So I took those 261 people and flipped their values. Made 0 to 1, 1 to 0. That's it, nothing else. And then, so if you see only between 0.5 and 0.6, between 0.50 to 0.60, everybody was inversed. Everybody was inversed. So if you see, there's this dip and something, a hill shape, something on the graph. So I took the dip and pasted it on top. So I took anybody between 0.40 to 0.50 and converted them to 0.50 to 0.60. That's it. And if you see that, all my sensitive features, all my fairness matrices has gone down. All. Now, very interestingly, you will ask that what should be the size of the diameter? How do you know that it should be, if my 50 is the threshold, it should be 40 to 70. How do you know that percentage? What should be the size of the diameter? I do not know. So what I do, I use this graph. I take all the sizes from 0 to 100 and make this graph. So if you see, anything around 10 to 15% my cost goes down. Anything around 10 to 15%, all these values goes down. So I know the size of the diameter should be 0.10 to 0.15. So if you have a 0.50 as your decision boundary, it should be what? 10. So 40 to 60 or 35 to 65, something like that, right? So you can optimize your threshold from the first graph and optimize your theta, which is the diameter of the circle, from this graph, right? Anything else? So that was what I wanted to show before I move to the last couple of slides. Anything here? So all of you have seen the GitHub, you don't have all this. Because this will not miss, it will be tough to understand just by just reading lines of codes. Any questions here? No? Okay, great. So let's see. We stopped on this slide, right? Okay, so did we see all this? Did we see what is statistical parity, disparate impact, predictive parity, all those 9 matrices on the bar graph? Did we see Reeving method for binary? We saw for binary, the first box. Did we see optimal threshold, single and double, 2 different threshold for male, female, different threshold for cost and everything, right? And we also saw additive counterfactual fairness in classification and in regression along with weights, along with counterfactual unfairness method. Now what is the last box? With weights and without weights? You can take an additive counterfactual method, put the weights and make an additive counterfactual method again. You can combine 2 techniques. And this was for multiple optimal threshold. And then we saw this, where we saw reject option classifier. We saw theta, which was the diameter, what should be the size of the circle. And it's a non-modeling approach. I did not make any model. I took my actuals, I took my predicted, and that's it. I did not make a model, did not touch your model, and just without using any model, I made the data fair or the output fair, right? So that was the thing, and we used credit risk data. Anything, guys? So any doubts here before we conclude, or we open the house for questions answer? Yep. Anybody? Questions? No? Great. Okay, so I'll be outside in case you would like to get in touch on this topic. So we have been doing this exercise for a lot of our clients in financial services, where we went and educated them what is fairness, got fairness implemented them or for them on multiple use cases, mortgage, non-mortgages use cases. So few of the clients wanted the entire data science thing, few of them wanted the last part and the first part only. So we have been doing this. So what we realized that it's not about how to do it. We are not very sure about when to do it. We are not even aware that this needs to be done. This became a very hot topic after Apple Card made this noise. So we would not want to be next to Apple Card, make a noise, somebody comes, file a litigation that you made an unfair decision, and then we raise a flag that, hey, we need fairness, right? So this has to come proactively. Industry has not adopted it much yet because it's still in research. So it will take time for the industry to come on this. So yeah. So it will take time for the industry to adopt, but however, this is what we are looking at right now. These are multiple techniques. There are techniques for unsupervised learning, clustering, PCA, another thing. But this gives you a flavor of what is fairness mathematically, how fairness ties up with accuracy, how accuracy ties up with cost, and on different part of data science lifecycle. So if you are starting a new project, you can play with the data. If you are already in modeling, try ACF. If everything is done, do the reject option classifier. So we have all the 3 options. We are not asking to reinvent the wheel or go start the modeling process again, right? So they can be different things at different part, different combination. And again, all this fairness matrices and accuracy matrices is very, very confined to the use case you are doing. So right, for example, in this use case where you have credit risk, what's my false positive? And if I give loan to somebody who would not pay me back, is dangerous. But what about cancer medicine? It would be, so in cancer medicine, it is better to give medicine of cancer to people who do not have cancer rather than not giving medicine to people who have cancer. False negative. So there I would like to optimize my false negative, not false positive. It's something like I get medicines, give it to everybody. So everybody who have cancer get cured and everybody who do not have cancer just get a headache. That's it, right? But in bank it will be other way around. So if you go and give loans to everybody, like a cancer thing, So all those who are not going to pay you back, you're going to go for a huge loss. And you can't even go and say, I'll not give loan to anybody, then better shut down your bank. Right? So those are the things which we need to be very, very careful. So if you follow, if you see my LinkedIn, I've written a lot of articles. On ODSC blog also, there's this one article which talks some brief about this. So thing is, these are all in research. If you take all these words, start Googling it, research papers, but then there's no implementation as such. So if you see, almost all the codes were manually written. We did not use a library because they exist, I guess, no one library which fits the bill, right? Great. So thank you guys for being a patient audience, and it was nice interacting. Please be in touch, write to me in case of anything you want to connect over this concept or outside this concept, and I'll be there for the whole day, around maybe for one and a half hour and 5 o'clock today, and we'll see you over emails, and maybe we'll can have a small catch up at our office. Okay. Thank you so much.